So, again we are in first year laboratory of physics of IIT Kharagpur. So, today I will demonstrate the coupled pendulum. So, this is the setup for this coupled pendulum. So, this is a simple pendulum, this is one and this is another simple pendulum, right. So, pendulum, for simple pendulum, you know this, there is a mass is hanged with a jelly thread, but here it is hanged with a light rod, it is a light rod, okay, and this mass is heavy compared to this rod. So, this is a simple pendulum. Okay. So, we can find out the time period of a simple pendulum, how to find out that, you know, right. Just I will displace it, and I will just use stopwatch. So, we have stopwatch. So, I have to just start 1, 2, 3. So, this way I will count the number of oscillation and collect time, and then I can find out the time period for this simple pendulum. Similarly, I will find out the time period for the another simple pendulum, similar, it is the same mass, same length. So, it is expected that time period will be more or less same, okay. But we have to find out the time period for this one also. So, we will find out the time period of this one. So, now these are two individual simple pendulum, we want to couple them, okay, and then we want to study about this coupled pendulum. So, this we will couple these two pendulum using this spring. So, we will do the experiment for two spring, spring 1 and spring 2. So, I have two spring. So, we will repeat basically the experiment for the second spring. So, we will do the experiment for first spring and repeat the experiment for second spring. Okay. So, let me tell first what we are going to study in this coupled pendulum. That means, we should know the theory about this coupled pendulum and what will be the working formula for this experiment. Okay. So, coupled pendulum equation of motion, I have two pendulum. So, displacement of this one, if it is x, this displacement of other one we are taking, that is y, then since they are coupled, so we have to displace we will assume that both are displaced, one is displaced by x, another is displaced by y. So, then equation of motion of this pendulum, okay. So, this displacement of this one is x, displacement of this one is x, but it is coupled with the second pendulum. So, that effect will also come here. So, thus it is coupled. So, equation of motion will be m x double dot d2x by dt square, right, equal to, if it is just one pendulum not coupled, then what it will be. So, mg x by L, mg, this is restoring force, mg x by L, this is restoring force. How this term is coming? Mg, so this is the, so when I displaced, so this mg is acting just vertically down. Now, restoring force is basically just this component. So, you can take two component, one is perpendicular to this, another component will be perpendicular of this component. So, what I want to mean, so if this is the vertical mg, so this now this angle is theta with this vertical, what is the original position vertical, now force is parallel, now with this angle is theta. So, mg cos theta this acting this way, okay, and mg sin theta will act this way. So, mg sin theta is basically restoring force and its direction is opposite to the displacement, right, opposite to the displacement. So, that is why this negative sign is there, mg sin theta. Sin theta for small theta you can take as a tan theta or theta. So, tan theta or just theta will be this by this. Okay. If this angle is theta, so the tan theta is this x by this L. So, that is why here is a x by L, mg x by L, and minus sign this restoring force is working opposite direction, right. So, similarly for y also, this one also minus mg y by L. So, if they are not coupled, so this could be the equation for these two individual one. Now, since they are coupled, these two additional terms has come. Now, these two term how it has come. So, now they are coupled. I think this spring, I have to attach this spring. I have to attach this spring. Okay, I have attached. Okay. Now, this is the position. So, this spring I have kept in such a way. So, just originally it is just natural length. It has natural length. It is not extended or compressed. Okay. So, it is a natural length. Okay. Now, if I displaced this by x and this by y, now what will happen? This spring, if I displaced both by x equal amount, so this spring will be in the same length. It will not be neither either compressed or extended. Okay, it will have the normal length. So, spring constant basically constant force per unit length, restoring force per unit length. If spring does not compressed or extended, so it will not apply any force. So, if it is equally displaced, so there will not be any force, okay, restoring force. If it is displaced this by x and this by y, so that one is extended by x minus y, right, x minus y or y minus x, then multiplied with the spring constant. Okay. Spring constant is force per unit length. So, x minus y or y minus x, that is the ultimate compression or extension, right. So, that is why this x minus y times k, so that will be restoring force, due to this spring. Okay. So, that is why these two terms has come. How this sign has come, you can find out. Okay. So, if x is greater than y, so this x minus y is positive. Okay. So, this spring means compressed. Now, at this displaced position, this spring is compressed. Okay. So, now I am studying this one, taking equation of this one. So, due to this extension of the spring, okay, so it will apply force, restoring force in this direction. Okay. So, that is why this opposite to the displacement, this force restoring force opposite to the displacement, that is why this negative sign will come. So, similarly here also. Okay. So, this equation for that one, I have to think about this one. So, you will get this. Okay. So, this is the equation of motion for coupled pendulum, right. From here, so omega 0, here omega 0 g by L, omega 0 g by L, omega 0 square, time period naturally it is 2 pi by omega 0. Now, here you see I cannot solve this equation just like this, because it has two two variable x and y, okay, I have to decouple them. So, there is a procedure to decouple them. So, this just I have written in terms of omega 0, in terms of omega 0 taking the g by L omega 0 square and equal to this k by m this part. Okay. Now, if I redefine the variable capital X equal to small x plus small y, capital Y equal to small x minus small y. If I define these two variable and put here, then I will get this equation. Now, you can see this equation only this x, capital X is involved, this equation is only capital Y is involved, and this equation now is decoupled. Okay. So, it is like these two equation is just it is a equation of simple harmonic motion. Now, I have basically for this coupled pendulum I have two motions, one variable is capital X and another variable is capital Y. Okay. And so, this frequency of them is one is omega 0 and another is omega 1 square root of this, omega 1 square root of this I have written somewhere, yes, omega 1 square root of this. So, we will have two frequency omega 0 and omega 1, this system, this coupled pendulum will have these two frequency. Now, these two frequency whether I can realize individually one of them, so it will oscillate with one frequency or one of them of course, and then whether they will it will oscillate and it will have this both component. It will have this both component of omega 0 and omega 1. Okay. So, that is why there are three cases. Case 1, it tells about the in phase mode. Now, imagine that if y equal to 0 means x equal to y, right. Y is we have defined x minus y. If y equal to 0, then x equal to y, then this equation x equal to y, y equal to 0, naturally this equation will not be there. So, this now this it is converted to a single equation, only this equation. So, solution of this equation or the frequency of this. So, this is the equation of simple harmonic motion and its frequency is omega 0. So, this compound coupled pendulum will oscillate with this frequency omega 0. Okay. So, condition is that then we will tell it is in phase mode, in phase oscillation, and for condition of this one to get this in phase oscillation, condition is we have to displace both in same direction with equal displacement, okay, because x equal to y. Okay. So, we will study this condition x equal to y and it will be displaced in same direction. Second condition is out of phase. Okay. If x equal to 0, then x equal to 0 means x equal to minus y, x equal to minus y, right. So, if so, then x equal to 0, this equation will go, only this equation will be there. And for this equation, so frequency, so these are simple harmonic motion, frequency is so the second case is out of phase mode. If x equal to 0, then x equal to minus y, x equal to minus y, right, x equal to 0, then x equal to minus y. So, then this equation will go, okay, x equal to 0. So, only this equation will be there. So, that means this system, this coupled pendulum will oscillate with only with this frequency omega 1, with this frequency omega 1, right. So, this is a out of phase mode. So, this also we will study. So, when we will get this mode, x equal to minus y means when this x this will be displaced in this direction, it has to be displaced in opposite direction. Okay. And this magnitude means value of x and y has to be same, x equal to y, but it is opposite, negative sign is there, means in opposite direction. Okay. If we displace like this, then this equation is telling we will get out of phase mode and its frequency will be this. Okay. Now, these two modes of oscillation are called normal modes, and omega 0 and omega 1 are called normal frequency. So, this will measure, we will study. And then another case is resonance. Another case is resonance. So, now this was our equation, x double dot plus omega 0 square x equal to 0, y double dot plus omega 1 square y equal to 0. So, this was our equation, right, where x is x plus y and y is x minus y. And solution of the general solution of this one can write x 0 cos omega 0 t plus phi 1 and y equal to y 0 cos omega 1 t plus phi 2. Okay. So, this is the general solution where phi 1 phi 2 are phase, omega 0 and omega 1 their frequencies, okay, and x 0 and y 0 this is the amplitude of oscillation. Now, if x 0 equal to y 0 equal to say 2a, some amplitude I have given, means this both. Okay, so let me first explain. If I consider x 0 equal to y 0 equal to 2a, some amplitude, and phi 0 phi 1 equal to phi 2 equal to 0, if this is the condition, then if I apply here, so basically I will find out x, small x equal to basically from here half x plus y equal to, I will get this, and from here you will get 2a cos omega 1 minus omega 0 by 2 t cos omega 1 plus omega 0 by 2 t. Okay. Similarly, y, small y will get half x minus y equal to this. Okay. So, what does it mean? I got small x equal to this, means displacement of first pendulum, okay, is coupled with the second one, of course. So, displacement of first one will vary like this, displacement the other one at a time. So, it will vary like this. Okay. It is cos function and it is sine function, right. What does it mean? When this will come, this cos function, when it is for a particular time, okay, say at a particular time this is 0, then this will be maximum for that angle, because you know cos 0 is 1 and cos sine 0 is 0, right. Cos 90 degree is 0, sine 90 degree is 1. Okay. So, that means when x will be maximum for a particular angle, this omega t, okay. So, the other will be 0. So, other one will be 0 if it is maximum or vice versa. So, this scenario we should see here. Okay. So, that means when one is at 0 position, other will have the maximum displacement, okay, and vice versa, or we will get this scenario in repeated manner. If one is disturbed, other one is at rest. Okay. So, that means this which one was disturbed, that will come at rest after some time, and in the meantime other should have the maximum displacement, right. So, that is why it is telling, equation is telling. And another part you see here, two cost term is there. So, one term, this term we can take amplitude and this is the cosine term. This is the amplitude and this is the sine term. Okay. So, this so in amplitude this cos term and sine term is there. That means amplitude will vary also periodically. So, it will have two frequency, one is omega 1 minus omega 0 by 2, that is basically it is a frequency of the variation of the amplitude, So, this basically this frequency is called beat frequency, beat, and this other one is basically is the frequency of the coupled pendulum. So, individual frequency. Okay. So, individually it will as if it has frequency, that is for coupled pendulum, and amplitude variation, periodic variation will be there, and that is basically it is a beat frequency, beat we will observe beat also. So, here that is why omega c we have written equal to omega 1 plus omega 0 by 2, omega b we have written that is equal to beat frequency, that is equal to omega 1 minus omega 0 divided by 2. Okay. So, omega you can convert to in terms of t time period. So, that is why t 0 and t 1, that here I have shown the relation, what will be t c equal to 2 t 0 t 1 by t 0 plus t 1 t b t 0 t 1 into 2 divided by t 0 minus t 1. Okay. So, and degree of coupling is defined by like this. So, this chi is t 0 square minus t 1 square divided by t 0 square plus t 1 square. So, here you can see we have to just basically measure the time period t 0 and t 1. Then all other things we can calculate, time period of this, what is the beat time period, what is the couple time period for the coupled pendulum. Okay. So, that is the experiment we will perform. So, here basically here what we have to do, observation and calculation. We will use the stopwatch. What is the least count of the stopwatch, that only I have to note down. Least count of the stopwatch is in this case 0.01, okay, 0.01 second. So, that we will note down. Now, before coupling spring 1, okay, time period of the pendulum 1 as I showed you. So, that we have to note down. Time period of the pendulum 2, that we have to find out before connecting this one. So, I will note down. Okay. And then I will do the for coupling condition, I will do the experiment that I will show you, and for spring 2 again I will take out this one spring 1, then again I will note down the time period of pendulum 1, time period of pendulum 2, okay, before coupling. So, now we should go for after coupling. So, I will just show for spring 1, for spring 2 you can repeat the experiment. What I have to find out? Actually, I have to find out t 0 and t 1, right. This is the, so t 0, what is this in phase mode, in phase mode I can find out the frequency, that is the t 0, and out of phase mode, so whatever the frequency I will find out, so that is the t 1. Okay. So, that is what I will find out. So, for each one I will take 3 reading and then average of that t 0, average of that here out of phase t 1. So, then basically I can calculate this coupled mode, this is T c, yes, T c I can calculate. Okay. So, I will calculate, if I know that t 0 and t 1, I can calculate T c, T b and chi. So, that is there. Another, experimentally I can find out this, this is basically TC, experimentally TC and TB also I can find out from this experiment. Okay. So, let me show you. So, in phase, let me show you in phase means x equal to y, that is what the theory tells. So, here I have put scale because x equal to y and in same direction. Okay. For that I have to approximately I have to displaced equally. So, let me just so it's I will take it it's around 37.5 and it is around okay. So, I will displaced by 7.5. So, if I do that, that's okay. So, I have to yes. Okay. So, I displaced both of them equally x equal to y and in same direction. Now, I have to take time period for this one. So, I know this is in phase mode and spring will not be compressed or extended. So, I will collect okay. So, I have to make it 0 and then okay, start 1, 2, 3, 4, 5. So, this way I have to collect say 50 oscillation and for this what is the time and then you note down this time and this number of oscillation and find out T 0. Second, out of phase, what was that? X equal to minus y. So, I have to go in opposite direction, but equal amount of displacement. So, again I will go okay, this I think I will take this way and this other way okay. In opposite direction, I have taken in opposite direction, I have to find out the time period T 1. So, again let this reset. So, now I will start okay. 1, 2, 3, 4. So, count it okay. Number of oscillation you take 40, 50 and this note down the time okay. So, this way you will find out the T 1. So, T 0 and T 1 we have measured. Now, let me show you the resonance condition okay. Let me show you resonance condition, very interesting. Resonance condition, what was the condition? So, condition was what was the condition? I have to that was 2a okay, x 0 equal to y 0 equal to 2a and phi 1 equal to phi 2 okay. So, basically what I will do, I will keep one fixed, other one I displaced by 2a okay. Okay. So, as I told it will be switch over, it is now at standing condition, now other one is maximum displacement okay. If I start you see it will be stopped and it will have the maximum displacement okay. Then just opposite. So, energy is transferred from this one to this one. Now, you see it is a standing condition. So, here two time period, one is individual one, you know, individual one okay, and another is that beat one, amplitude variation as I told okay. So, this time period I have to calculate. So, same way we will calculate this time period okay. So, this one and another this stopping okay, for beats okay. For beats I have to find out time period. So, when it stopped I will start okay. When it stopped I will start, when it stopped I will start Okay. I think I have to stop. Okay, reset. It stopped. Okay. If I start from there, I will start time now. Okay. So, when it is perfectly stopped, that start. So, then time to come to the rest this pendulum, and then it will come to the this rest the other pendulum. Okay. So, how many they are coming in rest? So, that number you have to note down, and for that what is the time. Okay. So, now from there you will find out the time period for bits. Okay. So, this is the experimentally we calculate, we find out this time period for TC and TV, and theoretically also you can calculate and then you can compare of them. Okay. This is the very interesting that one is stopped, another is have maximum displacement, okay, or maximum amplitude of the displacement of the oscillation. So, this way it will be going on, it will be going on. So, this is the phenomena of this coupled pendulum basically, okay, and very simple, but interesting, and basically whatever equation we solve, that we verify, and from that equation you got the time period, etc., and with this simple setup we can verify them. Okay. So, I think I will stop here. Thank you.